So, we continue with our discussion on the development of bottom segment enthalpy balance equation, and if you look at the board, that is where I have left you during my last lecture, that after doing a series of simplifications, which of course is not complete as of yet, okay, we have arrived at this particular form of the enthalpy balance equation. I have used a compact notation for the enthalpy term, enthalpy of the blast term. I have told you that when the enthalpy of the blast will be a contributor or supply heat to the furnace, or when it will absorb the heat, and I said the threshold temperature is 1200 degree centigrade as per the expression that I had written in my last lecture for EB to be. The way we have cast it, we would like, we will treat in this course EB to be a positive parameter, or worst come worst, it is 0 where the blast is being introduced at. Now, we are all set to make two more good steps before we arrive at the final. The first step would be to split the enthalpy of these compounds. There are three compounds, CO, CO2 and FeO, into their respective components, and then structure the equation, explain to you the demand and supply concept, and structure the equation not in the input output form, but in a demand supply form. These are the two tasks remaining before we can arrive at the final equation. So, let us see 1.06 Fe, this term, how can you split it? So, H naught 1200 Fe 0947, that is Austite, and that is equal to, we have 1 mole of Fe. So, this is 1 mole of Fe and H naught. So, we will say Fe, and that is solid, and that is at 1200. So, I have got 1 mole of Fe, I have brought it to 1200. So, what it must be having some sensible heat and standard from its pure state. Then I have 1 mole of oxygen. So, I will say that half of H naught O2 1200. So, the standard enthalpy that I have taken from handbooks, which regards O2 as the mole, and I have used half of its value, because I am considering that it is, we have half mole. O is my molar basis, not O2. So, therefore, we have only one atom of oxygen, and then we have how when this combines together and forms Austite at 1200 degree centigrade, then at 1200 Kelvin, sorry, then we produce 1.06 moles of Austite, and that would be the heat of formation of Austite, Fe 0947 O, and that is 1200 Kelvin. So, these are the three components. I have got iron, 1 mole of iron, then 1 mole of O2, both at 1200 degree centigrade. I have let them combine together, and because it is an exothermic reaction, we will see that the H of value will be taken to be a negative quantity, because heat is going to be released and lost from the system, that we will do later on. But these can be split into three different components, but they are the standard enthalpy and this is the heat of formation. Same expression we can write for carbon monoxide also, H naught carbon monoxide at 1200. So, I will take 1 mole of carbon, okay. So, H naught carbon 1200. I will take half mole of oxygen, okay. Then I will take half H naught 1200 oxygen O2, and then I will have 1 mole of CO, which is produced. So, it is the heat of formation, and that is equal to 1200. So, I have written carbon. So, I should write it here, oxygen and 1200, and then I have 1 mole of this heat of formation, and that is equal to carbon monoxide at 1200. Similarly, I can split CO2 1200 also as H naught C 1200 plus. Now, I have O2, so half factor is not necessary. So, it is H naught O2 1200 plus 1 mole of carbon dioxide. So, it is H heat of formation of carbon dioxide at 1200. That is what it is. So, I can split these terms. Now, if we manipulate this, we can see that, let us look at this 3 terms particularly, that one term is this, the heat of formation term. Which has formed from, resulted from this particular term. We can make a box, and in that box we can put one as this term, first term. The second term will be combined 2a and the left hand side, they are going to be treated together, 2b. And then we have the third term, that there is 3a with this term as 3a and this term as 3b. They can be treated together. And if we do this, then what we have, that we are going to, this term is appearing on the left hand side. So, we are going to transfer this term on the right hand side. Okay. So, in one side I will just maintain these 2 terms, 1, 2a, 2b and 3a, 3b. That is my one side. So, that is what it is. It is 1.06, okay, and then heat of formation of, if you take it to the other side, okay, reverse the sign. So, this must be given a sign of minus HF, and that is Fe 0947 heat of formation, because I have taken it to the other side. Then if I treat the 2a and 2b, okay, so 2a will have a negative sign because it is going on the other side, and then I have 1 mole is common, and then I have H naught Fe liquid already existing term, okay, at 1800 minus H naught Fe solid at 1200. That is another term. And the third term is going to be associated with C by Fem, and that is going to be is equal to H carbon in this dissolved state at 1800, which is already there on the right hand side, and then I have H not C at 1200. This is one box of all the terms I have created, and then I will take all the terms, and this I will make the right hand side of the equation. Okay. You can imagine that we will write it, if you transpose it, and then we have on the other side, we can therefore say that we will have from here one term will be remaining, this is this particular term. Okay. So, they remain on the left hand side, though this will remain as a positive side. This term is to be taken to the other side, this term is to be taken to the other side, this term is to be taken to the other side. Okay. Rest all of the terms I have treated, EB, this term remains here itself. Okay. And then NaC term also will remain in this term. So, we are trying to get, what we are trying to do? We are trying to get all terms positive in this system. Whatever is there on the right hand side, whatever is there on the left hand side, each term calculated will have a positive value. That is the whole objective of doing this particular exercise. Now, so therefore, if you look at this particular exercise, then one box is this. What is the remaining box? The remaining box is, I can say that this is going to be this term, because C by Fem I have taken to the other side, and from this 3 terms originated, 2 I have already shifted as far as it is shown here. So, what I am left with is this particular term. So, that is half H naught O2 1200. And then this is, I have taken, this I have retained here, and this is done now. So, one term is there, this is there, this is there. So, therefore, this term I have already embedded in the expression itself. So, this term will change its sign, this term will change its sign because I am taking it to the other side, and this term will also. So, these are the balance terms. Okay. So, now the input output I can, there is no input output now the way I have structured it. So, one side of the equation will contain this, and if I have not done any mistake, then in that case we have the other side of the equation which will contain this particular term. So, now if we look at this, let us first address this. Since this value is negative, heat of formation is negative, so this value will come out to be a positive quantity. This is at 1800 degree centigrade, this is at 1200 degree centigrade, this is also positive. Similarly, this is 1800, this is 1200, so this is also positive. C by FEM is already known to us, so this is a positive quantity. Heat of formation is known to us. This enthalpy increment is also known to us from thermodynamic data book. Similarly, this is also known to us, and this is known from the given composition. So, therefore, I can say that this term is a known parameter in the blast furnace, idealized blast furnace operation itself. Now, how is iron produced in this, in the scheme of the given idealized process? That Woodstite has entered at 1200. I have split Woodstite into iron and oxygen. So, I got iron at 1200. That iron now needs to be heated up to 1800 with the liquid state, and into this carbon has to be dissolved. There are three components in the iron extraction to get this product. 1 mole of iron in which 4.3% carbon is going to be dissolved. I have to do 3 different steps, that is break Woodstite, take iron to 1800 second step, and then dissolve carbon which is already at 1200, make carbon at 1800, and then at 1800 you dissolve carbon. And that is what is this particular term, that you are supplying the heat of formation to break the bond between iron and oxygen. Here you are now taking that iron from 1200 to 1800 degree centigrade, and here what you are doing, the carbon that is entered, okay, that how much carbon? It is this much carbon which is entered from 1200, it has entered at 1200. So, you will take it at 1200, from 1200 to 1800, and then you dissolve it in iron. So, these are the 3 components, and these are, you have to supply energy for all these processes, and then only you can get 1 mole of Fe, in which you will have C by FEM, or 4.3% carbon, or 0.2121 molar ratio. So, therefore, this is the requirement of the process of the idealized iron blast furnace process, and this we call as a DWRZ, the demand of the Woodstite reduction. What are the units of this term? This term is kilocalorie per moles of Fe, because heat of formation is, for example, this is kilocalorie per mole of Fe, 1.06 okay, is going to be, you have kilocalorie per mole. So, therefore, this is just moles of oxygen by moles of iron. Okay. So, therefore, 1 mole will cancel out, and this unit will have a unit of here of course, the moles are there, 1 number of moles. So, moles of iron. So, therefore, this term can be represented as kilocalorie or kilojoules, sorry, not kilocalorie, kilojoules per mole, and this mole is kg moles. As you can see, that is what is the enthalpy content. So, all these terms are H naught values are expressed per mole basis. So, all are kilojoules per mole, and then you multiply it by the moles, and then you get the moles in terms of moles of Fe, per mole of Fe. That is what you are going to get. For 1 mole of Fe to produce, that is what is the number of kilojoules that is going to be necessary. And this on the right hand side, when you represented this as the demand term, this essentially represents the supply term. Okay? How? So, the oxygen is getting into the system at 1200 degree, it is supplying heat, carbon which is coming into the system which is supplying heat, and this is the enthalpy supply, and this is the heat of generation because of carbon monoxide and carbon dioxide. Okay. So, therefore, this side will say that we have represented now the equation as demand is equal to supply. This demand term can be calculated the moment I give you that what is the ore composition, the moment I give you that how much of carbon, silicon, etc. can be calculated, and this demand term will not just contain 3 terms, it can contain 30 terms depending on whether, because the thermal demand will increase. For example, if you have slag formation, if you have limestone calcination, if you have silica reduction, you have phosphorus reduction, you have manganese reduction, all these components are to be added into this, and then the actual demand term in the blast furnace, including the loss, could be calculation. How accurately you can calculate this term depends on how you will be able to, how accurately you will be able to establish the third equation itself. Now, so we have said enough about this term, we will not going to discuss any further, for it is sufficient for us to know that all these terms are known from the handbook. So, if I substitute the value for hematite, hematite to reduction woostite, then it comes out that the dWRZ is going to come out to be so many kilojoules per mole of Fe, kg mole of Fe. I will not say always explicitly kg mole, but we must understand that it is not gram mole that we are, okay, that is what is the value of. To produce 1 mole of Fe containing 4.3% of iron, okay, that is the kind of demand, bottom segment demand that one has to fulfill, and that demand has to be balanced by the supply term. So, the supply is equal to this. Now, let us see how we can manipulate this supply term. As you can see here, that the supply term contains, for example, with NAC terms. So, this term exists here. So, we have 1, 2, 3, 4. So, let us now consider on this. On the supply term, you have 13 different terms associated with the moment you supply here 3 terms. So, you have 3 terms for here. So, 3 into 2, from this term itself you will get 6 terms, from this you are going to get 6 terms, 12, and then you are going to get 1 term. So, there are 13 terms that will result once the standard enthalpy is substituted in terms of the respective enthalpies, and these terms are all going to be associated with the coefficient NAC. Okay? And then in addition to this 13 terms, there is going to be 1 term here, the second term here, and the third term here. These are the 3 additional terms that we are going to see in the whole thing. Let us now manipulate that 13 terms that we see on the right hand side, okay, on the supply term. So, we will just open up the value. So, we have NAC into H naught 1200. So, we will write C 1200, I think, that is what it is, notation C 1200. And now, we have NAC, and then for carbon monoxide we have 2 minus O by C. I will not write any more gas extract reduction zone, just for saving some time. So, this is essentially a gas extract reduction zone, and we also know we will substitute at an appropriate time what is the value of this. This I have shown to be thermodynamically, from thermodynamic consideration or for equilibrium consideration, that O by C gas extract reduction zone is equal to 1.3. That is what we have seen. We will substitute at a later stage. And then we have, this is for carbon monoxide, and then we have carbon monoxide. So, H naught C 1200 plus half H naught oxygen 1200 plus heat of formation CO 1200. That is what it is. And then we have minus NAC, another term, and this is going to be O by C minus 1 into H naught C 1200 Okay, this is CO2. Okay, so therefore, I would say this is half is there. So, there will be no half here, H naught O2 1200, and then we have plus heat of formation of carbon dioxide at 1200. That is what it is. Let us open up the bracket. Okay. So, we can do it here. For example, we can write NSC 1200. So, let us expand this. So, we will get 2 times, we will write down 2 times, first if we multiply, then we will get this term, okay. Then we will get 2 times of this, if we multiply it, okay. And then this is plus this, and then we will have added up on this, the bracket is not closed. So, the expansion term is going to be, then I am going to erase this, okay. And then the expansion term is going to be minus O by C gas into H naught C 1200, that was the term, minus O by C gas H naught oxygen 1200, and there should be a factor of half here, minus, then we have 2 is absent here. So, we have O by C gas into heat of formation of CO2 at 1200. So, these 6 terms have come from this term. So, I will say, so let us do this, and then we have NaC, and there is minus term. So, simply I have multiplied this, there was this Hc, then half this, and then when you multiply with the first factor, this becomes 2, the half cancels out, and this becomes 2. Similarly, when you multiply with O by C, now the sign becomes negative. So, we get O by C, Hc, and then the factor half again appears here, and then O by C. Similarly, if you do this here, then we will have, I will erase this, so that we will have minus NaC, okay, and then we have first we multiply. So, we see O by C gas into Hc 1200 plus O by C gas into H naught 1200 O2 1200 minus plus O by C into heat of formation CO2 1200, and there are 3 additional terms, and that is going to be just Hc 1200 naught, okay, plus H naught, and these are going to be all minus. So, I need not do the signs, okay. So, multiply with 1. So, the same term will be there, H naught O2 1200 minus heat of formation of CO2 comma 1200. So, I have now one term, I have opened up this bracket, 6 has resulted with a negative sign, 6 have resulted with a negative sign, and now I can simplify this. Okay? And if you simplify this, then you can see that, for example, now we can remove this, because this has already been expanded. So, let us see that we have, there are several terms which can cancel out particularly, okay? And then we can visualize here. For example, let us see that H naught oxygen, from carbon we have got an H naught oxygen term here. So, within this we are going to now find out what has cancelled out. So, H naught oxygen 1200 and H naught oxygen and this is the term that has cancelled out. This is the term that has cancelled out. So that I don't do a mistake. There are carbon terms also which should get eliminated, if not totally, it should get eliminated partially. So, we have seen here that NSE 1200, you can imagine this. Okay, if you open up the bracket, then this and this will become positive. Okay, and as we already have here a 2 times, okay, which is negative here. So, this term and this term treated together will cancel out. So, this is 2, this is 2, and this is 2. So, we are now seeing that this term has vanished actually. So, this term has remained here, EB, NOB, and then that term is also remaining half NOB H naught O2 1200, and we will see to what this comes out to be. So, now we have, as you can see here, the heat of formation terms NSE. Okay, these are my heat of formation terms, and there is another, there are 4 heat of formation terms. So, one is this, the second is this. In every expression there is 4 such terms. So, okay, and then we have 2, and then heat of formation term is here. I will do it with yellow. This is heat of formation term, and then finally we have heat of formation term of carbon dioxide. So, 4 heat of formation terms are there, just so that 4 heat of formation terms. We have cancelled 13 terms were there. So, we had cancelled out 1 okay, and 2, 1 and this 1, this 2. So, 1, 2, 3, 4 and 5. 5 terms have been cancelled out. So, there are 4 additional terms which are going to be remaining, okay? And these additional terms are this. Okay. So, I will put a star here. This additional term is this, then there is 1, 2, this additional term is here, and this additional term is here. There are 4 additional terms. That is the account balancing. Okay. 4 heat of formation term, 5 terms have cancelled out 9, and there are 4 such terms which are associated with O by C. So, let us see the heat of formation terms. Okay. So, if you open the bracket, so if there anything else which is cancelling out among the 4 terms that I have written, let me see, half O by C HO2, and we have HC HO2 plus. Okay. So, this is 2 terms are associated with carbon, okay, and O by C H 1200. So, this is one term, and this term is going to cancel out. If you look at it, O by C gas HC 1200, O by C gas HC 1200, this is going to be, when you open up the bracket, this is going to be minus and minus positive, and this is going to be minus. So, this term is also going to be vanishing. This is the 3, and this term is going to be vanishing with O by C gas with this particular term. So, 7. So, 2 terms are remaining. What are those 2 terms? These 2 terms are associated with oxygen, and as you can see here that this term is NaC into oxygen positive, this is going to be a negative term, and this is a negative positive term, negative negative positive. So, the net contribution of this is going to be half can be subtracted. This is the same term, one is half, the other is plus. So, therefore, we can say that this term is bigger, this is with a negative sign. So, I would say that this term is going to manifest as, let me see once again, that it is going to be minus NaC into O by C, from this minus NaC into O by C gas into oxygen. This is the term I am talking about now. Concentrate on this term and concentrate on this term, which are the remaining terms. Okay? And this term is going to be NaC, O by C, and HC, H naught 1200, oxygen 1200, and that term is plus because we have minus here. If you open it up, then this is a minus sign here. So, this is half the same term O by C gas into H naught 1200, sorry, oxygen 1200. So, I can say that this is plus, this is minus. So, I would say I will just do it like this, and then I am going to erase this out. So, on top of this we have 4 heat of formation terms. Now, let us see that what we have here. We have these 3 terms here, 1, 2 and 3. All are associated with, should be actually, H naught oxygen 1200, H naught oxygen 1200. They are all associated with this. Okay? And half is there. So, if you take the half, all these terms if you manipulate, you take half H naught oxygen 1200, then what you are going to get? You are going to get, okay, here for example, so oxygen, I think I have made a mistake somewhere, that should come out to be, anyway I am going to get here. So, we have NOB is a positive term. Okay. We are going to get minus NaC into O by C gas, and this term actually which was remaining from the outside, I think I missed a factor of 1.06, because this term has originated oxygen 1200 from because if you remember 1.06 Fe0947 O. So, therefore, that should split up into 3 parts, and the oxygen component is going to be what? 1.06 multiplied by half multiplied by H naught oxygen, and that is 1200. That is the component of oxygen which should result. So, I think I missed a factor of 1.06 here. So, I would take that this term is equal to 1.06, okay? And you can check it, when you will do the derivation yourself, you will see that indeed what I am saying is that I have missed the factor of 1.06 somewhere. So, if you do this 1.06 here, and then what happens? You see, these 3 terms results into the bottom segment oxygen balance equation. That is the beauty of the derivation. Now, these have been done with regard to an idealized blast furnace operation. So, I have got it 1.06, but here you are going to get, for example, not 1.06 when you are dealing with non-ideal blast furnace operation, when you have silica reduction, phosphorus reduction, etc. You will see your derivation will not yield 1.06, because your oxygen overall oxygen bottom segment oxygen balance equation will show you that for metal earth reduction this is not 1.06 or something higher than 1.06. So, this 1.06 will not always result. This 1.06 has resulted for only ideal blast furnace operation. This value, all these derivation steps, if they are done correctly, in that case you would get the same value here which you have actually gotten in the bottom segment oxygen balance equation. So, therefore, the moment you apply the bottom segment oxygen balance equation, okay, this term vanishes, and therefore, we would say that we are now left with only 5 terms as far as the supply is concerned. EB is remaining, and then from there the 4 heat of formation terms that I have indicated to you, and that remains here. So, therefore, we are getting there, do not get restless. So, this is the term, supply term has remained, and 4 from here we will get 4 terms associated with the heat of formation, and these terms are going to be, for example, if you look at it, minus NAC, and what are the heat of formation terms? The heat of formation terms are within the square rectangular portions. So, minus NAC, if you do this, and then we have heat of formation is taken, heat of formation of carbon, heat of formation of carbon. So, this is first 2 boxes are carbon monoxide. So, it is going to be carbon monoxide 1200, and if you manipulate this term minus, okay, NaC, if you keep it here, and then we have, we are not opening the bracket. So, the sign is not going to change. So, we have first bracket is, this is 2, and then this is the second term is here minus O by C. So, we will see, we will get this. So, we will maintain this term as negative, and then we will write the same thing 2 minus O by C. Yes. And then we have minus NaC. So, we will see that we can, to save on some time, I will take the NaC common, and looking at this term I can generalize that this is going to be is equal to O by C gas into minus 1 into heat of formation of CO2 1200, and the bracket is closed, and this is what it is. This term is always greater than 1, this term is always greater than 1, this value is a negative value, this value is a negative value. So, therefore, this term is going to come out with a positive sign itself. So, if you substitute the heat of formation of carbon monoxide, which is 113 kilojoules per mole of per mole or kg mole, okay, and if you substitute for carbon dioxide, it is 395,000 kilojoules per mole, and now you substitute at the final stage O by C is equal to 1.3. So, it becomes NaC into 1.3. So, NaC into 0.7 multiplied by 113,000 kilojoules, okay, and this enthalpy has to be also calculated in kilojoules. So, that I can equate it with the demand term, because what is sitting on the left hand side is the dWRZ term. So, therefore, I can say that this term is going to be minus NaC multiplied by 0.7 multiplied by minus 1130, because heat is evolved, it is lost from the system. So, the heat by convention we will substitute a negative value. Similarly, here it is going to be 0.3, because it is 1.3 minus 1.3 multiplied by heat of formation, and there you are going to substitute minus 395,000 kilojoules per mole. And if you do this substitution, then we get that the entire term with their appropriate value, with the heat of formation substituted and the O by C oosterite gas reduction zone put into the value, we are going to get this term boiling down to simply NaC will remain here, and we will get all numerical values here. 2 is a numerical value, O by C will be a numerical value, this is a numerical value, and that numerical value will come out to be 198,000. So, you see, with such hard task, we have arrived at a very nice equation. dWRZ, demand of the oosterite reduction zone, is equal to NOB EB plus 198,000. So, in the morning I started, when I discussed started discussing the development of the bottom segment oxygen balance equation, I have written two equations, the overall oxygen balance equation and the bottom segment oxygen balance equation, and I have shown that there are two equations, independent equations, and there are three unknown variables, and you must understand, as far as this equation is concerned, the enthalpy given the temperature of the blast, the enthalpy of the blast can be calculated. Okay? So, therefore, dWRZ is known to us, as I have indicated to you. This will always be calculated. Your job for a blast furnace operation is only to calculate the dWRZ, and then you can, this right hand side is not going to change in any case. It is the demand that is going to change, the right hand side will remain, whether it is a non-idealized blast furnace operation or an idealized blast furnace operation, because the simplifications that we have done are applicable across the board. So, therefore, I can say the whole task is going to be calculation of the dWRZ. So, having known the dWRZ, demand of the austerity reduction zone, having known the blast temperature or EB, I have here an equation which correlates then NOB with NSC, which are the same variables which is applying or appearing in my oxygen balance equation. So, I would say that I have three equations now, and these three equations will constitute a comprehensive framework which will allow us to calculate NSC, NOB, as well as the top gas composition correctly. Now, if you have the last point that I want to make before I conclude today's lecture, we have, for example, the bottom segment oxygen balance equation, NOB plus 1.06 is equal to 1.3 into NSC. So, what we can do here is that this equation and this equation can be combined, because these are both bottom segment equations, one is oxygen balance and the other is enthalpy balance. So, we can derive a combined equation which we call as a combined bottom segment oxygen and enthalpy balance equation. This is no new equation, this is just a mathematical equation. For we will see why we want to combine the equations, because there is a reason for it. Combined enthalpy bottom segment enthalpy and oxygen balance. And we are going to eliminate that NOB term, and therefore, we are going to write dWRZ, the demand of the austerity reduction jet, is equal to enthalpy of the blast multiplied by 1.3 NSC minus 1.06. Okay. So, NOB we have substituted, and then we have 198,000 into NSC. And this essentially gives us that we have NSC, if you come, this is (1.3) EB, and this is going to be minus 1.06 EB. And suppose if we have the blast introduced into the furnace exactly at 1200, the enthalpy of the blast becomes equal to 0, as I have seen, because it is enthalpy of the blast is defined as heat content at TB minus heat content at 1200. The moment TB is set to be equal to 12, by definition enthalpy of the blast becomes equal to 0, and if enthalpy of the blast becomes equal to 0, this gives, if EB is 0, or other words TB is equal to 1200 Kelvin, then we can say that we get a very simple explicit equation on the basis of which the coke rate of the furnace can be calculated very conveniently once the demand has been computed. So, this is what it is. Okay. So, we have derived 3 different equations, and these 3 different equations, as I have I will summarize now, and this equations is, one is our overall oxygen balance, and that overall oxygen balance equation, and that is NOB plus for idealized blast furnace preparation with pure hematite as the ore, no slag generation, and this is what it is. Number 2, bottom segment oxygen balance equation, and that gives us NOB for the same idealized condition is equal to 1.3 NSC, and the third equation that we have derived is the bottom segment enthalpy balance equation, EB equation, and that is what is the value here. Now, as we have to see now that what is how you can convert this information in the graphical representation. For example, you have derived an equation in terms of enthalpy, okay, and these are enthalpy, while all the terms here are NOB, number of moles of oxygen per mole of, we made a plot. If you remember the plot on the ordinate, we have number of moles of oxygen by per mole of Fe, that is what we are plotting. Here we have that is the value in the blast, 1.5 is the value in the O, and we are plotting in O by C. Now, we have defined the third equation here, which mathematically gives us sound, but how to visualize this, because the units of these terms are kilojoules per mole, for example, all terms are kilojoules per mole. So, how can you superimpose the information contained in this equation into the graphical picture? So, this is our overall blast furnace line, okay, and this is our same line itself, but I am drawing it with bottom segment oxygen line, and this is the point here, which is say 1.5, and this is 1, and we have, as I have indicated, that and this point is the 1 W point. And we want to now see that how the information contained from the bottom segment equation, enthalpy balance equation, can be converted into superimposed on this particular equation, but that this equation contains all the terms in kilojoules per mole, and these are all moles of oxygen per mole of iron. So, therefore, it is not straightforward to substitute this or manipulate this. So, we have to do some things, and that is why basically what I have done is I have written this particular equation, that I have combined the oxygen balance and the bottom segment enthalpy balance, so that I can visualize the terms with in appropriate units. For example, if we now say the purpose of deriving the combined enthalpy balance and material balance equation for the bottom segment is to translate the information contained in the enthalpy balance equation into a form such that the necessary from the information can be superimposed on this particular point itself, graph itself. And here what happens is we can now do dWRZ, okay, plus 1.06 and I will explain this enthalpy of the blast, and this is going to be equal to NAC. And this is going to be 116,000 divided by 283,000. So, this is the figure that one can manipulate here, and I would say that this term, this is 16,940 I think, yes, 169,000, 169,000, this is. Why I have manipulated this, then I can add 1.0 and then I can subtract 1.0 and then I put a negative sign, and I can restructure these equations like this. 1.06, this is of course EB. The combined enthalpy balance equation can be structured in this particular fashion. Why I have structured it? How does the values, arbitrary values, these values are not quite arbitrary, as I will show to you in my next lecture. Okay? I wanted to give it a form, and that is what you see, that I have got it 1.3, that means the O by C ratio I have got it, and the O by C ratio essentially multiplied with this becomes oxygen per mole of moles of oxygen per mole of Fe. That is what is the product of the two terms, and therefore, this term should also have the same units, and we have converted. This term is oxygen per mole of Fe in this. Well, I could have got this term also 1.5 mathematically. I have added 1.06 and subtracted 1.06. Somebody can say that, sir, mathematically 1.5 addition and 1.5 subtraction is also possible, but I would say that these numbers are not arbitrary, because this is an O by Fe ratio that we are, because we are trying to convert the equation into an O by C, and O by Fe ratio, there are only two values possible in the whole system. Okay? If you consider the top part of the furnace, O by Fe value is 1.5, the bottom segment O by Fe since is 1.06. Since we are doing a bottom segment enthalpy balance, only one O by Fe value is pertinent, and that O by Fe value we can making it physically realistic. This number 1.06 therefore is a mathematical and physical possibility. If we put 1.5 here, then it is mathematically right, but physically it is not possible, because in the bottom segment O by Fe 1.5 has no relevance at all, no higher oxides exist in the bottom. Similarly, this manipulation 1.3, this is the characteristics of the bottom segment, okay, and which goes with the exit gas itself, and rest is these numbers have come out because of the mathematical manipulation, and also here these are all associated with the heat of formation of carbon monoxide and carbon dioxide, as we will discuss later on. And now we can see Y2 minus Y1 is equal to m into x2 minus x1. So, we have structured it, and we are going to superimpose that point on this particular line now, in the next class, and then we will complete the discussion as far as the graphical representation of the combined enthalpy and material balance equation go. So, we will stop here.